Okay, so today we're going to take notes on section 7.2 on finding complex solutions. So that means both real and non-real. So complex is a combination of real and non-real solutions, which we also sometimes call roots and sometimes call zeros. Zeros in particular are what makes a function equal to 0, so that's what we focused on in most of 7.1. And so we're going to just kind of continue on with that idea of what we've done the last couple of lessons, different methods that we've learned for solving polynomial equations. And so let's look at the example that's provided in the book first. So if we start with this equation, x cubed plus 7x squared. If we want to find the zeros, that means we're really trying to solve the equation x cubed plus 7x squared equals 0. And so does anyone see any way we can factor that? Okay, so we can take out an x squared. So if we put an x squared out in front, we have x squared times x plus 7. We could also write that as x times x plus 7. The reason why I like to write it that way is because we can see now this is a third degree polynomial. And so since it's a third degree polynomial, we expect to get 3 solutions. And so by writing it this way, we see this one gives me x equals 0. This one gives me also x equals 0. And then this one, what would be the solution associated with the factor x plus 7? X equals negative 7. So we have these 3 solutions. We have a third degree polynomial, and so it should have 3 solutions altogether, and we see them all right there. And so we don't need to write the 0 twice. What I'm going to just say x equals 0 and x equals negative 7. But underneath the 0, I'm going to say this is a double root, which means it occurred twice. We see that over here. We see the x equals 0 twice. Okay, so we only need to list it once, but identify it as a double root. Yes?
Will we always have to identify it as a double root?
Yeah, well, because what we want to get to is a point where no matter what the degree of the polynomial is, we want to make sure we have the right number of solutions. So if it was a 4th degree, we want to see that there are 4 solutions. And so if one of them turns out to be a double root, then we want to specify that. Okay? Okay, so the next one. Okay, so we have x cubed minus 64, and that is a difference of cubes. X, or a cubed minus b cubed is a minus b, a squared plus ab plus b squared. So that's the difference of cubes formula that we saw a few days ago. And so since in this one a would be x, and b is 4, we're going to have x minus 4, x squared plus, what would the middle term be?
4x.
4x, and then the last term?
16.
16. B squared is 16. And so we have that factored completely now. If you tried to factor this one again, you could try all the different possible combinations, and you would see that it's not factorable. And so if that's not factorable, so far we only have one real solution. We have x equals 4 from this factor. So what we want to do is always take each factor and set it equal to 0. So when I set that equal to 0, that turns into x equals 4. That's a real solution. Now this one, when I set it equal to 0, I was unable to factor it, so the next thing to try is the quadratic formula. And so that's what we have here. We have that same equation. We're setting that factor equal to 0, and then identify a is 1, b is 4, c is 16. And so when we plug all that into the quadratic formula, we get negative b plus or minus b squared minus 4ac and that ends up being 16 minus 64. That's negative 48. And 48 is 16 times 3. So since it's negative, it's going to be 4i root 3. So negative 4 plus and minus 4i root 3. And then in the bottom we have 2a, and a is 1. So that's why we just have a 2 on the bottom. Okay? And then when you simplify this, 2 goes into all three of these numbers. So if you divide all three of those numbers by 2, you get negative 2 plus and minus 2i root 3. And then in the denominator, 2 divided by 2 is just 1. So we don't need to write a 1 in the bottom. There are our two non-real solutions. So we have one real solution up here, x equals 4, and two non-real solutions. If we write those out separately, you can see each one individually. 2 plus and minus 2 plus 2i root 3 is one solution, and x equals 2 minus 2i root 3 is the other solution. Okay? Is it negative? It is negative 2, you're right. Negative 2, negative 2, negative 2. Okay, so good. Thank you for catching that. Those are all negative 2's. Okay, so we have our, remember we started with a cubic, that's a third degree polynomial, and we have our three solutions, one real and two non-real. And so something that's good to note here is that whenever we have these non-real solutions, they will always come in pairs. You'll never have just one single imaginary root. They always come in pairs, and they're always conjugates of each other. So by conjugate, I mean the sign in between them changes. So it's negative 2 plus 2i root 3 and negative 2 minus 2i root 3. The complex roots always come in pairs, and they're always conjugates of each other. Okay, one with a plus and one with a minus. So we'll keep that in mind moving forward. Okay, and so the next example, C. The first thing we can do is factor out an x, and that leaves us with x cubed plus 3x squared minus 4x minus 12. Okay? And when we have four terms, what's one of the methods that we've learned for factoring when there are four terms? Grouping. So grouping doesn't always work, but we can always try it. So if we group those together, the first group, x cubed plus 3x squared, I can factor out an x squared, and that leaves me with x plus 3. And then in the second group, negative 4x minus 12, I can factor out a negative 4, and what's that leave me with? X plus 3 also. Now when these turn out to be the same, when this and this turn out to be the same, that means grouping is going to work. We got the same factor. So what we can do now is take that factor and move it out in front. And so we have x plus 3 out in front. And what are we left with when we pull those x plus 3's out of there? X squared minus 4. Okay? So then, can that be factored anymore? We still have the x in front from here. And what else can we factor? Yeah, the x squared minus 4 is a difference of squares. So now we have x plus 3, and x squared minus 4 factors as x plus 2, x minus 2. So now we have the whole thing broken down as x plus 3, x plus 2, x minus 2. So from this one, since we're able to factor it out completely, we have all four real zeros. So this factor leads us to what solution?
0.
X equals 0. The next factor, what's that tell us? X equals negative 3. When you set this factor equal to 0, you get x equals -2, and when you set this factor equal to 0, you get x equals +2. So we have 4 real solutions, or 4 real zeros. And the original problem was a 4th degree polynomial, so we found all 4 solutions, and all 4 of them happen to be real for this problem. Okay, questions? Okay, example D. X to the 4th minus 16. They give you kind of a hint there. How can we factor something like that? What pattern is that? Difference of squares. This is, so we can factor it as x squared minus 4 times x squared plus 4. And then the x squared minus 4 we can factor again. X plus 2, x minus 2, because that's a difference of squares. And so now we're factored completely. We have 3 factors. This one gives me a real answer when I set that equal to 0, a real solution. What would that real solution be? X equals -2. And this one? X equals 2. So that gives me 2 real solutions, or zeros. Now when we set this equal to 0, that's x squared plus 4 equals 0, so x squared equals -4. If I take the square root of both sides, I have to do plus and minus on one side. And so that gives me x equals plus and minus 2i. And so that's what we have here. X equals plus and minus 2i. So x equals 2i and x equals -2i are our 2 non-real solutions, or non-real zeros. Okay, so again, it was a 4th degree polynomial. We found all 4 solutions. 2 of them were real, 2 of them are not real. Okay, so this next example, we're not going to do any work on this one. I just want to talk through it real quick so you can make a connection between what we're doing today and what we did yesterday. So yesterday we learned to use the synthetic division method to test out different roots. Remember, we used the rational root theorem to come up with a list of roots, and we did that by looking at the factors of the constant term over factors of the leading coefficient, which in this case would be 1. Okay, so we look at, for this problem, we look at the factors of 8 over the factors of 1, and we end up with a list of plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 8. And then we would go through and start testing all of those. Okay, so it looks like here in this example they tested 1, and it came out with a 0 remainder, so we found a root on the very first try. And so that means that x minus 1 is one of the factors, and the remaining factor comes from these numbers. So that is x, it started with a 4th power, so now it's going to be 3rd power, plus 6x squared, plus 12x, plus 8. And so that's what we can put here, x cubed plus 6x squared, plus 12x, plus 8. And now, notice that moving on from there, a lot of the ones we did yesterday, after we found one of the factors, we ended up with a quadratic, and we were able to factor it or use the quadratic formula. But now we have a cubic. So now we have to think about different ways that we can solve cubics. We could try factoring by grouping, but it looks like, I think in this one, the grouping method isn't going to work. But we can continue on with the list of possible rational roots that we have up at the top, but our numbers at the top change because now we've reduced it to a cubic. So I just take these coefficients 1, 6 came from here, 12 came from here, 8 came from here. And so we repeat the process, but we use our new coefficients now. And then it looks like they tried 1 and it didn't work. They tried -1, it didn't work. They tried 2, it didn't work. They tried -2 and that did work. We got a 0. And so now we just found another factor. So we have the x minus 1 from what we did previously. Now from this one we just found a new factor, x plus 2. And what would our remaining factor be? Where do we look for that? Elishba? Yeah, we look right there, and that tells us that our remaining factor is x squared plus 4x plus 4. And so now that is factorable again. So x squared plus 4x plus 4. At that stage, when you get to a quadratic, you either factor it or you use the quadratic formula. In this case, it factors pretty easily. X plus 2, x plus 2. And so look at what we have now. We have x minus 1, x plus 2, and then this is also x plus 2, x plus 2. And so instead of listing out x equals 1, x equals -2, x equals -2, x equals -2, instead of listing the same number 3 times, we can just simply say the zeros are x equals 1 and x equals -2, but -2 is a triple root. And again, the reason why we do that is to show that we did actually find all 4 solutions. This original problem was a 4th degree polynomial, and we did find 4 solutions. It just happens that one of them is a triple root, so it occurred 3 times, and then the 4th one is then x equals 1. So we have one single and then a triple root. So that adds up to 4 roots total. Any questions? Okay, so we'll skip down to the bottom of page 537. I'd like you to go ahead and try problems 5 and 6 in your groups. Those watching the video, just press pause and try to work through problems 5 and 6, and then press play when you're ready to see the solutions worked out. Okay, so for number 5, first we want to recognize that this is a difference of cubes with a equals 2x and b equals 3. So when we factor that, we get 2x minus 3 times 4x squared plus 6x plus 9 equals 0. And so then we want to take each of those factors and set them equal to 0. So 2x minus 3 equals 0 when x equals 3 halves. So we just found one real solution. Now for the second part, when we write 4x squared plus 6x plus 9 equals 0, you can try factoring it, but it turns out it's not factorable. So then the next thing is to use the quadratic formula with a equals 4, b equals 6, c equals 9. And so then that gives you x equals -b plus and minus the square root of b squared minus 4 times a times c over 2 times a. Okay, so that ends up being x equals -6 plus and minus the square root of -108 over 8. And when we simplify that, that turns out to be -6 plus and minus 6i root 3 over 8. And that can reduce to -3 plus and minus 3i root 3 over 4. And so this is, since there's an I there, that means there are 2 imaginary or non-real roots. So 2 non-real, and then up at the top we already found 1 real. So there's our 3 roots altogether. This was a cubic polynomial, and we found 3 solutions altogether. 1 real and 2 not real. Any questions on that one? Yes?
Is b equal to negative 3?
No, it's a difference. So what are we subtracting? We're subtracting 2x cubed and 3 cubed. So if you're using the difference formula, you would just say b equals 3. You could use the sum formula and then say b is negative 3, and that would work as well. Okay? But you can't do both. You can't use the difference formula and call it negative 3.
So everything has to be positive.
A and b are always going to be positive when you use the sum of cubes and difference of cubes formula.
Okay.
Okay? And then number 6. We always want to look for the easy things first. So the easy thing I see first is that all the terms have an x. So I factor out the x. That's x cubed minus 13x squared plus 55x minus 91. So we already see one real solution. X equals 0 from this. Okay? Now we have a cubic polynomial left, and what we have tried in the past, when we have 4 terms, we can try grouping. Grouping ends up not working with this one because we don't get the same factor when we factor things out of these 2 groups, and so grouping doesn't work for this one. So the next thing that we try is what we learned yesterday, which is listing our possible rational zeros. And so we need to think about the factors of 91. And the factors of 91 are, so m could be plus and minus 1, plus and minus 7, plus and minus 13, and plus and minus 91. Those are all the factors of 91. And n is just plus and minus 1. And so this becomes our list, because m over n is the same as just the list of m. And so now we need to remember that we already have one solution, but I'm going to take the x cubed, that's going to be 1, negative 13, 55, negative 91, and we can start with 1 and try that. So when I try 1, bring down the 1, multiply and add, negative 12. Multiply and add, 43. Multiply and add, and what is that? Negative what?
48.
Negative 48. So 1 didn't work. So now we try negative 1. Negative 14. And then 14 plus 55 is 69. And negative 69 and negative 91 is negative 160. That one didn't work. So now we can go to the next one, 7. Bring down the 1. 7 and negative 13 is negative 6. Multiply, you get negative 42. Add that to 55, and we get negative 13, or just 13, positive 13. 7 times 13 is 91. Add that to negative 91, and we get 0. So we just found a root. So now we know x equals 7 as another real root. And we also know the remaining factors. So now we can say that our polynomial p of x could be written as x times x minus 7. And our remaining factor comes from these coefficients right here. That is x squared minus 6x plus 13, which again is not factorable. So how can I set this equal to 0 if it's not factorable? Quadratic formula. It would be x equals negative b plus and minus the square root of b squared minus 4 times a times c over 2a. So x equals 6 plus and minus. What do we have here? We have 36 minus 52, negative 17. Does everyone agree with that? Is that negative 17? Negative 16? Oh yes, it is negative 16. And so then that is 6 plus and minus 4i over 2, which is 3 plus and minus 2i. And so now we see that we have x equals 3 plus 2i, and x equals 3 minus 2i. So we have our two real solutions here and two non-real solutions here. And so 4 altogether. We had a 4th degree polynomial, and we just found all 4 solutions. And so I think we'll stop there.